You can think of a vector in simple terms, such as a list of numbers where the position of each item in this structure matters. In machine learning, this will often be the case. Another way to interpret these elements that is relevant to linear algebra is to think of a vector as an arrow with a direction dictated by its coordinates. It will have its starting point at the origin, the point 0, 0 in a coordinate system, such as the xy plane. Then, the numbers in the parentheses will be the vector coordinates, indicating where the arrow lands. As you can see, we moved from the base by 2 units to the right on the x-axis and then by 3 units to the top on the y-axis. Every pair of numbers gives you one and only one vector. A vector is then an object that has both a direction and a magnitude. Let's try and break this concept down. We know that a vector has a starting point, which we call the base or origin. The direction is dependent on a set of coordinates that in itself is essential for defining this element. The landing point defines the direction of the vector v. Magnitude is the size of the vector, and it is also a function of where it lands. Providing context will indicate where this can be utilized and make the understandings of such notions more accessible. For example, if you are analyzing the height and weight of a class of students in this domain, a two-dimensional vector will represent each student. Here, v1 represents the height of a student, and v2 refers to the weight of the same individual. If we only know how to define vectors, one way to carry on moving forward will be to try to combine them or to multiply them by a scalar. On this lesson, we will cover two operations with vectors, the addition of vectors and the multiplication of a vector by a scalar. Let's start with the addition of vectors. Given two vectors, v and w, we can define their sum, v plus w, as a translation from the edge of v with the magnitude and direction of w. Did you just shit yourself with all the mathematical terms? If so, don't worry. These are just fancy terms for a simple concept. What we are doing is simply creating a clone of w that will then have as a starting point the edge of v instead of the origin. Then we will follow v and the projection of w like a path from the origin to the tip of v and then from the tip of v to the end. As with real numbers, the addition of vectors is also commutative, meaning that we can also do this addition by a translation from the edge of w with the magnitude of v. Analytically, the addition of vectors is performed by adding the elements of each vector with respect to their positions. On this particular case, we add the first element of vector v with the first element of vector w, followed by adding the second element of vector v with the correspondent one of the vector w. We have arrived to the last concept of the video, the multiplication of a vector by a scalar. Before jumping into the visualizations, I would like to introduce some notation. After all, we need to understand the syntax of mathematics. There has got to be a way to represent any number that belongs to the set of real numbers. For that, we will use the following notation. Let's start by the middle. The not-so-handsome E means to belong. Now, the cool-looking R represents the set of the real numbers. This particular set has all the rational numbers that you can think of. If you are thinking on some ludicrous number, such as pi, yes, it belongs to R. Finally, lambda is a variable, a generic letter that can accommodate any number, and on this particular case, it has to belong to R. On this occasion, we will go over the analytical part first, but visualizations will follow. Consider the vector v with the following coordinates. Now, for lambda, let's pick the value -2. To multiply a vector by a scalar lambda, one simply has to multiply each of the vector's coordinates by the value of lambda. Graphically, this is what happens to the vector v when we scale it by lambda. The vector v not only got stretched or scaled, but also changed its direction. What this means is that the value of lambda can impact two of the vector's characteristics, the length and the direction. There are 4 possible combinations of lambda that is worth exploring. The first one is when lambda is greater than 1. Here, the direction remains unchanged, but the vector's length increases. If for lambda, for example, we pick the value of 2, the vector v will see its components getting scaled by a factor of 2, which results in a new vector with coordinates 2, 6. The next value of lambda that we will cover is when the scalar takes as input greater than 0 but inferior to 1. On this situation, similar to when the value of lambda is greater than 1, the direction will prevail, but the length now gets altered differently. The vector shrinks. Let's pick for lambda the value of 1/2. Now, instead of the coordinates v doubling, they will be halved. So this version of lambda v will have for coordinates the values 0.5 and 1.5. Following, we have a value of lambda that is lower than 0 but greater than -1. On these conditions, the original vector v will not only shrink, but also the direction of the vector will change. To showcase this example, let's pick the inverse value of the previous lambda, so -1/2, meaning that the new set of coordinates is -0.5 and -1.5. The last case for a possible value of lambda that is present on the table we have already covered. It is when lambda takes values smaller than -1. When we introduced the concept of multiplying a vector by a scalar, we used a value of lambda of -2, meaning that not only the vector changed directions, but it also got stretched. With this, we have reached the end of this first lesson on linear algebra for machine learning. These are the topics that we covered: the definition of a vector, which is an arrow with a length and a direction that has as its base point the origin; the addition of vectors, which results in a vector that is a translation of the length of one of the vectors on the edge of the other vector; and finally, we covered a method to change or maintain the direction of vectors while altering their length, which is the multiplication of a vector by a scalar. In the next lesson, we will be going over a method to multiply vectors called the dot product.